Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Welcome back. Dear friends, today we will going to discuss moment area theorem. So this is chapter number 5 and our lecture is part number 6. Let me recall that in chapter number 9 part 1 and B we discussed deflection of beam. We determine the equation for slope and deflection. Then in part number 3 we discussed statically indeterminate beams. Then in part 4 we have discussed method of superposition, and in part 5 we have discussed singularity function for slope and deflection. So here we are going to cover the moment area theorem in order to find the slope and deflection. So let's start with the topic. In moment area theorem we will discuss first moment area theorem and the second a moment area theorem. So first we will discuss the first moment area theorem. So in this moment area theorem, geometric property of elastic curve can be used to determine the deflection and slope. So here the two terminology, geometrical property of elastic curve can be used for deflection and slope. So basically we will determine the slope and deflection equation by using moment area theorem. So you can see that this is a simply supported beam that is supported at point A and point B, and there are some loading that is acting on this beam. Clear? So in moment area theorem, if I define moment area theorem, so it can be defined as the slope or deflection between any 2 points can be found by using this moment area theorem. For example, if this is a point C and this is a point D, so you can find the slope between point C and D or deflection. Clear? So if you draw its bending moment diagram, so it will be like this. Again, this is a solved one. Now here we will define in new term, that is m over ei. So basically your bending moment is divided by ei. So if you divide the bending moment at every point in your this bending moment diagram and you divide it by ei, so you will get the same points, but the value will be changed and the graph will be the same as for bending moment m of x. Again I will repeat it for let's say this is the beam under the loading condition, and here it's a bending moment diagram. Clear? So if you divide every point of bending moment by ei and plot them again, so it will give you the same shape curve. Clear? And that is known as m over ei diagram, and that will be utilized in moment area theorem. So you can see that the load is acting on this beam, and here it is m over ei diagram. So now you can see that there is a point C and D. If you are interested to find out the slope and deflection between point C and D, so you can find the slope or deflection by using moment area theorem. Now what moment area theorem states? That the first moment area theorem states that this is the point C and point D, and you are interested to find out the deflection or slope. For example, slope. Clear? So you can see that slope theta dc, the slope of point D with respect to point C is equal to area under m over ei diagram between C and D. So this is a point C. Clear? There is a line point C and there is a point D. So the area under this m over ei diagram between point C and D will give you the slope of point D with respect to point C. So this is the first moment area theorem. Now if you recall from your previous knowledge, and you know that theta is equal to dy by dx. Clear? So if you take a derivative of theta with respect to x, so d theta over dx will become equal to d square y. Sorry, this is dx, not dx square. Okay, so d square y over dx square. And you know that this d square y over dx is equal to m over ei. How? I will show you as well. From our first and second part of this chapter number 9, we discussed that ei into d square y over dx square is equal to m of x. So again, d square y over dx will be equal to m over ei. So I have placed the value of d square y over dx square is equal to m over ei. Clear? So we can have d theta over dx is equal to m over ei. Or if you multiply dx on both sides, clear? So we will only get d theta is equal to m over ei, m over ei. Okay, so your d theta m over ei into dx. Clear? So if you integrate it, now here for integrations you have to define two specific points where you are interested to find out the slope. So again, if you integrate the both side, so for this you will, I have mentioned that this is a point C and point C. So you will have theta C to theta D. Rest you can take different points as well in order to find the slope. Clear? So again, from here you will have to write xc from xc to xd. Clear? xd. So if when you integrate it, you will get theta d minus theta c. Clear? Is equal to this term, which is equal to integral of xc xd m over ei into dx. Now this is integral of m over ei dx is the area under the m over ei curve between point C and D. Clear? So this theta d minus d c is actually, we can also write that as theta d slash c. Clear? So which means the slope of point D with respect to point C. Clear? I will show it here if you draw the deflection diagram of this beam. So it will be like this. Clear? So it will be like this, that is mentioned over here. So this is a point A and point B. At point A and point B there will be no deflection. Y will be equal to 0, but here theta will be equal to theta A and here theta B will be equal to theta B. But we are interested to find out the slope between point C and D. So you can see C and D. So if you draw a tangent to you draw a tangent that to point C, so that will be equal to slope C. So this you can see over here as well. I will show you, I will zoom it so that you can easily understand. Okay, so you can see this is a point C, and if you draw a slope, so this will be the slope. Clear? And this from here to this point, you can see if you draw a line, that is the for maximum deflection. Clear? So theta c will be equal to this. Clear? And if you draw a line tangent to point C, clear, and there will be horizontal line, so this will be theta d. Now what about theta dc? So again you can see this is a line, tangent line to point C, and this is a tangent line to point D. So the angle between this angle is actually theta dc. the slope of point D with respect to point C, and that is equal to the area under M over EI diagram between point C and D. So this is the first moment area. Clear? In our okay. So okay. So first moment of area theorem can be defined as the slope between any 2 points is equal to area under M over EI diagram between these two points. Here the points are taken are C and D, so theta DC is equal to area under M over EI diagram between C and D. Clear? We will also solve a sample problem on moment area theorem, and then you will be able to define, or you will be able to find out how to calculate the area under the M over EI diagram between these 2 points. So we will see in a while. Now let's move toward the second moment area theorem. So we will see what is second moment area theorem. So second moment area theorem states that the tangential deviation of C with respect to D is equal to the first moment with respect to vertical axis through C of the area under M over EI diagram between C and D. So this is the statement. Now let's discuss it, that what is the physical meaning of this definition, second moment area. So if you look, this is the deflection diagram of the same beam. So this point A and point B, clear, and there is a point C and point D. So we are interested to find out the total deflection between these 2 points, i.e. point D with respect to point C. Now you can see this point C is this point and point D. Let me zoom it as well. This is a point C, clear, and this is a point D. Now we are going to choose 2 small points between point C and D. Let P is the one point that is at a distance of x1 from this C. And if you draw a vertical line from C, so this is a reference line, so this P is at a distance of x1 from this vertical line from C. And another point P dash, this is at a distance of dx from this point P, and this dx is so much small that this point P and P dash are closer to each other. Okay, so again, if you draw a line that is tangent to this point P, clear, so it will also intersect the C at this point, clear. And if again you draw a point, if you draw a tangent from point P dash, so it and project it or extend it to this vertical line, so again this will meet with this vertical line at this point, clear. So this small distance is equal to dt, which is obviously a deflection between this point P and P dash, clear. So that is known as dt. Okay, so if you look at this line P and P dash, and this dx is very very small, so it means that P and P dash are very close to each other, means P dash each other. It means P dash and P are at the same point, clear. So this dte will be just like a circular arc. So if this is a P, clear, this is P, clear, this is P point, and P dash is also at, So this dt, this is dt. This is point P and this is point P dash. Both are very close. So angle between these two will be known as d theta, which is given over here. Clear? So change in slope. Clear? So from our equation of arc S is equal to r theta. So if you look at this, S is equal to dt. So dt will be equal to r. So here r is this distance x1. Clear? Because we have told you that dx is very small, so it will be, distance will be equal to x1. So dt is equal to x1 into this d theta. Clear? So this is the equation. Clear? Now you know that this d theta in our upper, we have seen that this d theta is equal to, this d theta is equal to m over ei. Clear? Here you can see this x will be x cancel. So d theta will be equal to m over ei into dx. Okay. So this d theta is equal to m over ei into dx. So you can see that is written over here that dt is equal to x1 into d theta. dt is equal to x1 into d theta. So x1 will be remain over here, and instead of d theta we have written m over ei into dx. Clear? So dt is equal to x1 into m over ei into dx. So again, if you integrate it on both sides, clear, and if you integrate it on both sides, and this will be equal to from x1 to x, okay, so if you integrate it on both sides, so we are generally interested to find out the slope and deflection from point C to D, or with respect to of point D with respect to point C. So again it will be from xc to xd and xc to xd. So in order to find out the total deflection or slope, so here we are going to find out the deflection. So we will talk about the deflection. So from xc to xd, total deflection is integral of td dt and x start from c to d is equal to integral of x from c to d into x1 or into m over ei into dx. Now this integral of dt from xc to d is known as tcd, and this tcd is known as tangential deviation of c with respect to d. So that how much deflection of c with respect to d, and this tcd is known as tangential deviation of c with respect to d, and it will be equal to integral of xc into xd, integral of xc to xd into x1 m over ei into dx. Now this is the second moment area theorem. Now we will go back to the definition, and now you will be able to understand what is the meaning of second moment area theorem. So the tangential deviation of c with respect to d, which is equal to tcd, is equal to the first moment with respect to a vertical axis through c of area under the m over ei diagram between c and b. So you can see this is point C, this is m over ei diagram that is represented over here. Clear? This is point C and this is point D, and this is the whole area under m over ei diagram between point C and D. So the tangential deviation of C with respect to D is equal to the first moment with respect to a vertical axis. So m over ei into dx is actually integral of m over ei into dx is the first moment of area, and x1 is the with respect to a vertical axis through C, and through this is the vertical axis, and this is x1's distance, which is the horizontal distance from this vertical line, and it is the distance of this centroid of this area with respect to this vertical axis. That is why it is known as second movement area theorem. So again I will repeat that tangential deviation of C with respect to D is equal to first movement with respect to a vertical axis through C of the area under M over EI diagram between C and D. So this is a point C and this is point D. So this is the total deflection of point C with respect to point D, which is TCD, and tangential deviation of C with respect to D. And how you will be able to find out this x1, what will be the location of the centroid of this area? Again, we will now move toward a sample problem in which you will be able to understand how to calculate all these things in order to find the slope and deflection. So you have to wait for a while. Okay. Application of cantilever beam and beam with symmetrical loading. So you can see this is a cantilever beam that is acted upon by a load P that is acting upward. Clear? So if you have a previous knowledge that if you draw at the end A is fixed support, clear? So at fixed support, so if you draw a tangent at point A, clear? So it means that slope at point A, theta A is equal to 0, clear? And at point D, if you draw a slope, so definitely it will make angle theta D, clear? So now if you are interested to find out theta D, so theta A can be taken as a reference because theta A is equal to 0. So theta D with dA, I am talking about theta dA, which means theta D minus theta A, which is equal to theta D. So if you take A as a reference, clear? So you know that theta A is equal to 0 because it is fixed support, clear? So theta D can be easily find out, which is equal to theta D minus theta A is equal to theta D. So cantilever beam, select a tangent at A as reference line, clear? So theta A here will be equal to 0 and theta D will be equal to theta dA. And this theta dA will be equal to, here I have written theta D minus A, which is theta A is equal to 0, which is equal to theta D. Similarly, you can see that deflection at this point will be equal to 0, clear? So deflection at this point D, which is equal to TDA, deflection of point D with respect to point A, clear? I will write it, TDA is equal to TD minus or YD minus YA, clear? So YA is equal to 0 at this point, so TDA is equal to YD, that is written over here. Now if you look at the another diagram, that is symmetric loading, so you can see there is a beam with a symmetrical loading. So if you draw the deflection curve, so deflection curve will be like this one, clear? And maximum deflection will be at point C, clear? So maximum deflection will be at point C. Now if you draw a tangent to this point C, clear? So here theta C will be equal to 0 because this line, tangent line, is a horizontal line, clear? So you can easily take this point C as a reference point because the theta C is equal to 0. Now you can find the deflection or slope between any 2 points from C to D. So if you are interested to find out the theta dc or deflection of point D with respect to C. So you can find out, so theta dc will be equal to theta D minus theta C. Again this theta C is equal to 0, which is equal to theta D. Clear? Or you are interested to find out the deflection at point B, so you can find the deflection and you can take C as reference because theta at C is equal to 0. So theta B C will be equal to theta B minus theta C, and theta C is equal to 0. So again it will be equal to theta B. Now you can find the deflection at any 2 points. So for example, if you are interested to find out the deflection at point P, clear, so that will be equal to YB, clear, and that is equal to TBC. Okay, now what does TBC means? TBC means YB minus YC. Clear? Okay, now okay, I think there is a mistake in that. Let me check it as well. Not B, this is point D, because at point B there is a support, clear, so deflection will be equal to 0. So again this is theta D, clear. So if you are interested to find out the theta D YD, so YD is equal to tau of D with respect to C, which is equal to YD minus YC. How? Because you can see this YC is equal to YD is equal to D with respect to C, clear. This is equal to TDC, which is equal to YD minus YC, clear. Or you can see that if you are interested to find out this theta D, wait a minute. Okay, so this from this point till this point C, this is TBC, which is equal to maximum deflection. There TBC means YC minus YB. Clear? This is the maximum deflection of point C with respect to point B. Clear? So if you are interested in TDC, so again this YD, or which is equal to TCD. YD will be equal to this is YD. This YD will be equal to TBC minus TDC. Clear? So tangential deviation of point B with respect to point C minus tangent deviation of point D with respect to point C. So you will get this YD, which is TDC. Clear? I hope it is clear to you now. Now we will move toward discussing bending moment diagram by parts. Clear? So if you look at previous slides, so these were the area that will be between point C and D of point C and D in M over EI diagram. So it is very difficult to find out the area of such type of curves. So basically here we have certain standards shape that is mentioned over here, and its area is also given, and distance from vertical distance of center from the vertical line is also given. So there is the first column is about shape, the second column is also shape, the third is area, and the fourth one is distance, location of its center from this vertical line. So this is a rectangle shape, so you can see breadth is B, height is H, and C is at center, so its area is BH, and location of its center from this vertical axis is C. Why we are taking this distance from this vertical axis? Because in second moment area theorem, so you need the distance of centroid from the vertical line. Again, there is a triangle, you can see the dimension, its area is BH over 2, and distance of centroid from this vertical axis, which is C, is given as B by 3. Similarly, parabolic equations, clear? So you can see this is a parabola, height h, breadth b, so its area is BH over 3, and its distance of center from this vertical axis is B by 4. Similarly, for cubic and for general higher order, so it will be again, this is a parabolic, so it is BH over 3, it is cubic, so BH over 4. Again, for cubic, y is equal to k power n. So for general or higher order, we can write n instead of a specific value, where y is equal to k power n, clear? And its distance, so there is a general formula for area and distance of center from this vertical line. So again, if you put, for example, parabolic, so n is equal to 2, so BH over 3, which is again same, and B over 4, which is same. Similarly, you can also use it for cubic and so on, clear? So what we will do is that we will use bending moment diagram by parts. So we will divide the diagram into parts. That the diagram, for example, the area under the bending moment may come like this. For example, there is a square shape or rectangular, and there may be a parabolic shape. So we will divide the bending moment diagram into parts, and then we will add it. So you will also see in the problem, in upcoming problem. So determination of change of slope and tangential deviation is simplified if the effect of each load is evaluated separately. So construct a separate M over EI diagram for each load. So for example, if we have a beam like this, where there is a uniformly distributed load that is given, and as well as there is a point load is given, clear? So you can calculate M over EI diagram separately for this uniformly distributed load, and for this concentrated load you can determine M over EI diagram for this concentrated load P. Then the change of slope DC is obtained by adding the area under the diagram. So you can basically, here you will apply principle of superposition that you have used in lecture number 3 or 4, clear? So you will use that concept, or you can use that concept in order to find M over EI diagram separately, and then you can add them in order to find the total slope and deflection. So this is for slope, and this is for deflection, that is tangential deviation. Bending moment diagram constructed from individual load is said to be drawn by parts. So if you first draw the bending moment diagram of distributed load and separately for concentrated load, so bending moment that is drawn for individual load is said to be drawn by parts. That is why it is known as bending moment diagram by parts. So now let's move toward a sample problem, and after that problem you will be able to understand the concept of moment area theorem. So sample problem 9.1. So you can see the beam, overhanging beam, clear? There is a support, roller support at point B, and there is a pin support at point D. So for prismatic beam shown, determine the slope and deflection at point E. So you are basically interested to find out the slope at point E and deflection at point E. Again, if you look at this beam, so we will not use here by parts method because there is same type of load given, clear. So we will use it in a single step. So for first step will be, our first step in order to solve this problem is to find out the reaction forces at point B and C, and this can be done by using method of equilibrium. So you will have to do it by yourself in order to calculate the reaction force at point B and D, clear. Then you have to draw the shear force and bending moment diagram, and when you get bending moment diagram you can divide each point of the bending moment by EI, so you will get the same shape uh, diagram, but it will be M over EI diagram. The shape will be the same, only numerical value will be changed, clear. Once you get the M over EI diagram, then you can use the area moment theorem in order to find the slope and deflection. So taking the tangent at C as the reference, evaluate the slope and tangential deviation. So let's move and solve this problem. Okay, so here they have calculated the reaction force at point B and point D, so you can solve it. The very easy steps are required in order to calculate this reaction force. So this beam is at a distance this reaction force is at a distance of A from this edge, and this reaction D is at a distance of A from this right side edge, and the distance between RB and RD is length L. So they have here they have shown the shear force and bending moment diagram. You can also draw it, and now you must be able to understand how to draw the shear force and bending moment diagram that we have already discussed and explained in chapter number 5. Here it is not necessary to draw the shear force, only you will require the bending moment diagram. So now you can see the bending moment diagram is like this, clear. Okay, so this is a bending moment diagram. So if you divide each point of the bending moment, for example this point low bending moment is this, and at this point the bending moment is this. So if you draw every point of the bending moment by EI, clear, by EI, so you will get the same shape curve, but the value will be changed. You can see here the value is minus WA square over 2, but here the value is minus WA square over 2EI. So only the difference is EI, clear. Rest the shape will be changed. Now we will use this M over EI, clear, in order to find the slope and deflection. So again we are interested, for example, if we are interested to find out the slope or deflection between any 2 points, you can find out. Again you can see we are going to find out the slope and deflection at point E. So you can see that this is point E, clear. So these are the bending M over EI diagram. So according to our first area theorem. So first area theorem, what does first area theorem state? I will show you that deflection between any 2 points is equal to area under M over EI diagram between C and D, clear. So that was about C and D. Now you can see this is a point C, clear, and this is a point D. Again, if you draw the figure of this beam, clear, so it will be like this one, clear, this one. Under the loading condition, there was a distributed load over here. So you can see this C is the maximum deflection, C is the point where the if you draw the tangent, clear, so theta C will be equal to 0, slope will be 0, and you are interested to find out the theta E, clear, theta E. So you can see theta E will be equal to theta C E, which is equal to theta E minus theta C. So again theta C is equal to 0, so you can calculate theta C. Again you are theta, I will write it, theta CE is equal to theta E, which is equal to area under M over EI diagram. Now here points are between point C and E. You can see the area under the ME diagram between point C and E is this area. I will shade it and I will then, this is the area. Clear? So this is area. Now how we will calculate this area? So let's talk about that. Okay. So you can see here we have two area between point C and E. One is from C to D, which is parabolic, clear, and the second one is a rectangular, clear. So we have divided this A1 and A2. So A1 is rectangular and A2 is parabolic, clear. So area A1 will be equal to, you know, the square area is its length multiplied by height. So length is L by 2, clear. I will show you, this is L. We have shown this total distance is L, so half will be equal to L by 2, clear. So again there is L by 2, clear, and its height is, if you draw the M over EI diagram, so you will get this value, which is equal to minus omega A minus WA square over 2EI. So length is this, length is L by 2 and height is this value, which is given over here. When you multiply it, area will be equal to minus WA square L over 4EI. Now the minus sign means that area is below, clear, and if A is positive, so it means it will be above this horizontal line. So A is equal to minus this one. Now A2 is parabolic, so you can see that the area of parabola is represented as BH over 3, clear, BH over 3. So B is this, breadth is A, clear, and H is this, again the same. This is B, breadth, this is height, and 1 over 3, and minus sign is again for downward area. So this is A2, clear. So when you add A1 and A2, this will be equal to theta E. You can see theta E is equal to theta C plus theta EC, which is equal to area A1 plus A2, and when you add both the areas, so you will get theta E, the slope at point E, clear, which is equal to this one. Now we will move to find out, I will repeat it here. If you want to find the slope, you will use the first moment area theorem. First moment area theorem. Because first moment area theorem is that the slope between any 2 points can be calculated and will be equal to area under the M over EI diagram between these 2 points. And if you are interested to find out the deflection, so you will use the second moment area theorem. Okay, according to second moment area theorem, it is equal to integral of M over EI into dx into x1 bar, clear, and x1 bar is the distance of its centroid from the vertical line. So this will be equal to total deflection, and again this will be equal to area into x1 bar, area under the m over ei diagram into x1 bar. So again, if you look at this point, so you can have ye, which is deflection, clear, is equal to total this ye deflection is equal to, with respect, if you are talking about with respect to c, because at c uh, there is a deflection. Okay, so you can see that we are interested to find out deflection of point E. So we are actually, there is a support at this point, clear? So this support, at this support, deflection will be equal to 0. So actually from this point to this point, this is ye, deflection of E, which is equal to total deflection, that is TCE, TEC, and this deflection I will show you here, from C to E, this is the maximum deflection, clear? And from this support D to E, this deflection is YE. TDE means YE minus YD. Now YD is equal to 0, so YD is YE, deflection at point E, is equal to TDE. Now this TDE is equal to YE, which will be equal to this maximum deflection, which is equal to TEC, TE/C, minus deflection this distance from C to D, D/C. There. Now you can see that we have the area m over ei diagram, clear? Again I will have to go back to that diagram. Here you can see TEC, which is the total deflection, and that is the area TEC. So from point C to E, so this area will be covered. Now the area of this will be equal to A1 and A2. So you can see that YE is equal to TEC minus TDC. Now TEC is this area A1 and A2. There. So area A1, this area A1, clear, and its distance of centroid from this vertical line. So we have to calculate this distance. Now this distance is equal to A, this distance A, and this is L by 2, and from this point to this point, this distance is L by 4. So A plus L by 4. Clear? So area into distance of centroid from a vertical axis. Now you have to take this area. So this is area A2, and its distance from the vertical line is, again this total is 2, and area center of this parabola from this vertical line is 3a by 4. From this side is a by 4, from this side it is 3a by 4, which is given over here, minus TDC. Now TDC is the area under CD, so minus this area multiplied by its vertical distance from this edge, this area. So this area is A1 minus area A1, and its is distance of centroid from this vertical edge is L by 4. That is given over here. So you have the value of A1. If you are confused, you can take the value of A1 and A2 from here. So you can put it and multiply it with A and L by 4. Similarly, A2, you can put the value of area A2, which is this one, and multiply by with this. It's A1 and you can simplify it. At last you will get the total deflection of point E is equal to minus WA cube over 8EI into 2L plus A. Now this is the general deflection equation for this beam. So if you have total length, the value of this, the value of A, the distributed load, and modulus of elasticity, and the moment of inertia of the beam, so you can get the numerical value of deflection of point E. So this was all about area moment theorem in order to calculate the slope and deflection. I will suggest you to kindly solve this problem by yourself as well as some other example, so it will help you a lot in understanding the concept as well. So in short, we will conclude that first moment area theorem will help you to find out the slope, and that slope can be found out by the area under the m over ei graph between the 2 points in which you are interested to find out the slope. Here it is point C and D, so area under the curve of m over ei between point C and D will give you the slope of point D with respect to C. In second moment area theorem, that is used to find out the deflection, and that is equal to tangential deviation of CA or any point with respect to another point D. Here it is D is equal to the first moment area with respect to a vertical axis through C of the area under the m over ei diagram. And rest you can watch this video again and again in order to clarify your concept. So if you have some other problems, you can choose this sample problem by yourself and can solve, so it will be better for you to understand. I hope you enjoyed my video. Thank you for watching.